No, excuse me, sir. I'm Rosie. Good morning, sir.
Morning. Hello. Is that for
Sir,
me?
for first section, I didn't post the attendance, sir.
No, that you can do it later. No issues.
No issue, ma'am.
No. You can do
Okay.
it later.
Okay.
Later, we will take the attendance in the afternoon session also, so you can do it.
Okay, ma'am. Thank you.
Okay, so let's get started, sir.
Sure, I can get started. No problem. I'm all set. I can't hear you.
Sorry, I think I was muted. Yeah. So good morning, all. So we are now going to get started with our second session of the day. So we have with us Dr. Sachin S. Gunthe from the Civil Engineering Department of IIT Madras. So welcome you, sir, for our talk. So I just call upon Bintu to give a quick introduction about our speaker. So Bintu.
Okay, ma'am.
Over
Thank
to you,
you.
Bintu.
So today, okay, ma'am. Okay, ma'am. So today we have the expert speaker, Dr. Sachin S. Gunthe from IIT Madras. So brief about him. Dr. Sachin S. Gunthe completed his master's from University of Pune in the year 2001. So he received his PhD in physics atmospheric stream from Indian Institute of Tropical Meteorology, Pune in the year 2006. After working for 5 years in Max Planck Institute for Chemistry in Mainz, Germany, he moved back to India in 2011. Since then, he is working at Indian Institute of Technology, Madras, India. Dr. Sachin also holding the positions such as Associate Researcher, Max Planck Institute for Chemistry, Mainz, Germany from 2014 onwards, and Associate School of Engineering and Applied Sciences, Harvard University, USA from 2014 onwards. Dr. Sachin honored with number of awards and recognitions such as Fulbright Nehru Academic and Professional Excellence Fellowship. Other recognitions are co-editor of Journal of Atmospheric Chemistry and Physics from 2015 onwards, co-editor of Journal of Atmospheric Chemistry from 2020 onwards. Then he is a reviewer of various reputed international peer-reviewed journals and funding agencies. Then more National Knowledge Network, an advisory group of MOEFCC to CPCB, principal member, Bureau of Indian Standards for Chemical Hazards, and he is also special invited speaker at various national international platforms on wide range of topics. Dr. Sachin has authored 53 papers published in top peer-reviewed journals. He has undertaken various sponsored research projects worth more than 21 crores in total. Dr. Sachin leads a research group of approximately 20 PhD students, number of master's students, and postdoctoral fellows. His research mainly focuses on aerosol biosphere climate interaction with special emphasis on impact of biological aerosols on climate and human health, cloud condensation nuclei properties of atmospheric aerosols, and impact on cloud formation and precipitation in the context of Indian summer monsoon. Today, Dr. Sachin will speak to us about emerging technologies for air quality monitoring. Respected sir, I would like to invite you to enlighten our participants with your expert lecture. Thank you, sir.
Thank you, madam. Thank you very much for your kind introduction. And it's always kind of a pleasure to get back to what I really like the most about the dissemination of the information or the knowledge, which at least I believe. I believe that my screen is visible to you and I'm audible.
Yes,
Can
sir.
somebody just confirm me that? Yeah. Okay.
Okay, sir.
Fine.
Okay.
Yeah. Fine.
Okay, sir. Okay,
Okay.
sir. Thank you.
So I would, before I start, I would like to thank the organizers for giving me this opportunity and inviting to share some of the domain knowledge about the air pollution and the emerging technologies which are being used in air pollution. Before I go into the topic and then really try to bring into your notice that what we do and then what we know about specific emerging technologies really with the air pollution, I would like to give you a glimpse that how this air pollution as a topic has really changed over the last 100 years. So what I'm going to do to start with, I'm going to show you a very small movie which basically covers the last, not last, but then the 100 years starting from 1900 to 2003, and then how the pollution has really increased over the period of time. So what you see in this movie is that the emissions basically from the mega cities, that the big cities across the globe, and then how those cities have started really polluting our environment. And then each year basically tells you that each plume, assuming that the plume which is coming from the cities has a lifetime of like 7 days or 20 days or maybe even higher, and then how it really is spreading across the globe over the last 100 years. So on this world map, try to pay the attention to the big cities like New York, London, Los Angeles, Delhi, Rio de Janeiro, Sao Paulo, Beijing, Sydney, so on and so forth, right? So let's try to have a very quick look on that. And then you see that this is the area just before the First World War when people, they have started looking into the industries and people, they have started knowing the Tokyo, for example, was very polluted at some point. You have Moscow, and then you have London, Vienna. This is the time when, after the First World War, really the industrialization, the burning, everything started coming up. Then you see some south in the southern hemisphere. You have these two big dots in South America, which are namely Sao Paulo and Rio de Janeiro. And then this is where, after the Second World War, the industries, they have started really coming up. Like you see Bombay, Kolkata, and then you see Delhi, and then a lot of countries in Middle East where you have a lot of oil things going on. And the pollution is no more a local problem, right? From early 1960s, it's not anymore the local problem, right? It has really become the transboundary, like what you emit and China is really traveling to the western coast of United States. What you emit in Delhi has repercussion on the Indian Ocean. And then you have you really have this era where the pollution has now started reaching the southern hemisphere, right? It's not only the uh, intercontinental, but it has now become the interhemispheric as well, right? And then as you reach by the end of 2003, and then it really goes in further, it's really becoming, and if I really stop the pollution in 2003 anymore, like you can see that the entire earth is really covered with this. So this was just calculated. I would like to thank Professor Jost Lelyfeld, who had shared this with me at some point of time, just to show that by modeling how really it has become the global problem, right? What I want to tell you is that what you really emit just in your backyard will have some repercussion on this one. Just to put that into the right perspective, that why do we really care what really boils down as far as the air pollution is concerned? Well, I mean, of course, there is no denial that like air pollution is causing the increase in global average temperature, and the global average temperature increase is the problem for everybody, particularly for the ecosystem, because everybody is important in the ecosystem. Even a one species getting extinct because of the global warming will have a very serious repercussions for the human being. And sometimes it is probably known that from the earth, if you remove any specific animal, have a repercussion that over the period of time it will affect the human. But there probably another thought process which says that if the humans are removed from the earth system, probably it's not going to harm any animal in the long term, right? So that's very important for us to understand why it is so. Again, to put it into the just to give you a perspective about why air pollution studies is important, rather than I go into the details of how do you measure it using advanced technologies. But why do we want to more and more air pollution, and why do we really care for the advanced technologies as far as the pollution is concerned? So as you just saw in that movie, it is not more just a local problem, but it is a global problem. So our quest for understanding the complexities associated with the air pollution is more and more. So Well, I mean, so these are again the repercussions. Like by 2020, already we know that like 750 to 250 million Africans are facing the water problem. Rainfed agriculture could decline by 2020, and that's what we basically see. Like increase in 20% in some part of South Asia, crop yields get badly affected. Glaciers, of course, that expected to decline, reducing the supply of meltwater to major regions, right? So 20 to 30% of all plant and animal species face increased risk of extinction, right? If there is a 1.5 to 2.5 degrees centigrade rise in temperature due to the air pollution. And then, and important part is that we as a researcher, obviously those who work in climate science or in air pollution, majority of us, we agree that all the scientific literature really do change, do indicate that the physical and biological changes in the natural world in the last few years. So I would like to dedicate this to Professor Paul Crutzen, who was a Nobel laureate who passed away this year recently. And I had an opportunity to work with Nobel laureate Professor Paul Crutzen, who has termed this new term called Anthropocene, because we have the different geological epochs right from the beginning of the Earth's, when the Earth came into the existence until now. We have a different geological epoch, and Paul Crutzen in 2000 has introduced this new geological epoch called Anthropocene. What it basically means is that we as a human are not currently living in an area where it is more of a natural, but the Earth is more influenced by the human activities rather than the natural system. So that's what basically is important to understand. Now let's quickly go and then try to understand what's the formal definition of air pollution. Well, anything which is kind of an introduction of harmful substances or products into the environment, which basically exceeds the certain limits, is called as the pollution, right? And there could be a various aspect of pollution in the environment, that the water pollution, air pollution, and land pollution. And organizers have kind of advised me to go. I would be focusing my talk mostly on the air pollution and then the requirements associated with that. This is just a glimpse that anybody had seen. I believe that everybody had seen these kind of pictures, more or less, not only on the internet, but let's say around you as well at some point of time. That's the air pollution. Now, of course, the formal definition of air pollution now, that the air pollutants are airborne particles and gases that occur in the concentrations that kind of can pose danger to the health and well-being of the organisms, or which can cause any sort of a disruption to the orderly functioning of the environment or to the ecosystem. That's the air pollutant, right? Now, when you look into the air pollution, for example, like you can then go on to categorize them into the two basic this thing, which is mostly the primary pollutant and then the secondary pollutant. So the primary is something which are emitted directly from an identifiable source, like you can really track back from where it is coming. Let's say, for example, a vehicular pollution or any sort of a biomass burning or a point source, for example, the factories which are coming. And then there are secondary pollutants which are then produced in the atmosphere when certain chemical reactions take place within the pollutants which are primarily emitted in the atmosphere. So that's basically, it's something good and prime example that the human knowledge has really evolved, right? We already knew when you were there probably in 1920s, you were already concerned only with the primary pollutants. But then there is obviously, now we are more concerned about the secondary pollutant, and then the prime example could be ozone, right? Because this ozone which I'm talking at the surface, not at the one which is in the stratosphere, that is a secondary pollutant, and it's really very dangerous one. So this is just as an example or a clear bifurcation about what do you mean by the primary and secondary pollutants. The major primary pollutant, just as an example, I have included them here, is the particulate matter, right? I would be using this term called particulate matter and aerosol very commonly, and then they both are the same. They are the same term. The only difference is that when an aerosol particle which is flying in the atmosphere, when it is collected on a filter for any sort of an analysis, It is called as a particulate matter because it is not anymore governed by any of the laws which can affect the behavior of an aerosol when it is suspended in the atmosphere. So that's the only difference between the particulate matter and aerosol. Then other examples are sulfur dioxide, nitrogen oxides, volatile organic compounds, which are probably one of the most studied and then the a really hot topic in atmospheric sciences or for the air pollution, that how do they behave, why they are important, and why their measurement is really important. So amongst all these, I would probably be spending little more time or more emphasis I would be giving through my talk about the implications of the VOCs for air pollution and related to their measurement techniques. And then, of course, you have carbon monoxide, lead, so on and so forth, which I would not be really going into the too details of that, right? Let's try to understand a little bit more about this air pollution because unless we really understand their sources and how do they are really interrelated with from the different sources, until then we would not be really able to apply or really acknowledge why the specific measurement technique is important for a specific source. Let's say, for example, I would try to give you a very simple example. When we are talking about the VOCs, like the volatile organic compounds, you may also go to the market and able to buy a simple VOC probe, which would probably cost you like 25,000 rupees. And then you are able to measure the VOCs. But at the same time, there is an instrument which is called PTRMS, like proton transfer reaction mass spectrometer, which would cost you like almost 4 crore rupees, right? Now, then obviously that's also try to measure that also measures the VOC, and then your VOC sensor or a VOC probe also measures the VOC, right? And then the obvious question then comes to the mind, like, then why should I spend 4 crore rupees when I get an instrument or a VOC probe which costs me like 25,000 rupees? Well, I mean, it would depend at what your source are and then how detailed information you want, right? There is definitely not an end to it. So coming back to that, like, so when I say that the primary sources, I am more concerned about the one which are created by the human, right? Because as I said that in this current geological epoch of Anthropocene, we are mostly having the primary pollutants, which are majority of the time coming from the human source, like combustion process, chemical processes, which we generally go through every time, nuclear or atomic processes, which is also one of the major sources for the pollution, roasting, heating, refining processes, and mining and quarrying and farming. That's also really one of the uh, uh, kind of a direct primary source by human. There is other source, of course, which are natural sources, like, for the primary pollutant, right? The primary pollutant can also be emitted by the natural sources, which is volcanoes. Like, that if you look into the volcano, it puts in lot of ash into the atmosphere, which has, again, a huge climate repercussions. You have breaking of seas, of course, right? That's really, again, a big source of various particles from the soil. You have pollens, terpenes, different VOCs, volatile organic compounds, tens of hundreds of thousands, which are emitted by the plants. Like, that the plants is the major source. Plants are the major source of the VOCs. So pollen grains, fungal spores, these are the natural pollutants. Then you have the forest fires, for example, right? It's a very important, by the way, the forest fires are not really bad. They are one of the very effective ways, what we call as an ecological cleansing, right? But then they are also very strong source of primary pollutants of dust, like, Saharan dust, for example, which is kind of carried away from the long distances. That's also one of the major source. Then the bacteria and viruses. But let's try to understand that these three last natural primary sources, like fire, blowing dust, and bacteria and viruses, are generally accentuated by human beings. Like, in the current sense, one could really always go on and then attributed these to be anthropogenic sources. Like nowadays, for example, forest fires are more ignited by the humans than the natural. Dust blowing, when you kind of the dust which is sitting there, which would otherwise not get suspended in the atmosphere if you were not to drive your car or vehicle there. So that's also has to be kind of termed as an anthropogenic source. And then the bacteria and viruses. And then one of the most prime examples of that is the current coronavirus, which is now emerging, that there will be a paper which will now soon be published in another few days, which kind of traces back the origin of the virus and kind of terms it that it was deliberately prepared or so sort of kind of created in the lab for whatever reason, and then it kind of sneaked out in there. Anyway, now coming back to the secondary pollutants, of course, the just as an example, again, like the atmospheric sulfuric acid is a prime example. Air pollution in urban and industrial areas is often called as a smog, where the visibility really goes down. It's also a prime example of the smog. The photochemical smog, a noxious mixture of very toxic gases and particles, is generated when there is a strong sunlight, triggers the photochemical reaction in the atmosphere. That's the ozone, which very famous Los Angeles and London smog, you know it. The major component of the photochemical smog is ozone. That's what we are more concerned. And then, although we know that we have made a huge progress in controlling the air pollution, the quality of the air we breathe remains a serious public health problem, because as and when we understand more about the chemistry and details of that, do we really have had made a progress about it? Well, we really not, essentially. Probably I'll not go into this definition, but since we are talking about the air pollution, it is very important. I would like to just put this slide for the orientation purpose, because I believe that the audience must already be aware of it, that we have categorized the pollutants as the criteria pollutants and non-criteria pollutants. And then I just want to put it because as such, it will not have any specific implication about the technology which you use for the measurement of these pollutants. But of course, it's always good to know what is the criteria pollutant and non-criteria pollutant, because of the toxicity associated with this. And that's the reason the hazard which is associated with the measurement process needs to be taken into an account. That's the reason we need to know what is the criteria pollutant and what is a non-criteria pollutant. It's a really complex process. Like if you take emission of various pollutants, they are emitted from various sources, and then obviously they affect the air quality on a larger scale, right? So what I want to give a key message from this slide is that this process is really a very complex process, and then everything is related with everything. I think Professor Ravi Krishna in the previous talk might have given you a various overview, although he did not really mention about the air pollution. Just to give you an idea that what are the different things which affect the air pollution. One is the population density, and the second is the topography, along with in combination with the meteorology, although I'm not going to go into the details, but just want you to understand that when you apply any specific advanced technique for the measurement, there are certain things you would always have to take an account of. Just to give you a spatial distribution, how India looks like, this is a prime example of the carbon monoxide or PM10 emissions or nitrogen dioxide emissions. Of course, the areas where you have the high population density or where you have the valleys, for example, like the Indo-Gangetic Plain or where you have more power plants, obviously the pollution is out to be more there. These are just a very typical examples of like how SO2 and NOx emissions are always very strong at the locations where you have urban locations, or particularly the power plants, essentially. And then of course the what do you call the high areas of the population density where you have let me just kind of look into that. Yeah, right here now. So sometimes you might want to see that like Kerala, which is very densely populated, can see that a very high pollution level there, right? Okay, dealing with air pollution in India, you all know that the Prevention and Control of Pollution Act, which came into 1981, and then the Environmental Protection Act in 1986, and then the Factory Act, that is an occupational hazard. Like, you know, there are certain protocols in the industries which they need to follow to kind of stop the employees from any sort of an occupational hazard. Not going to go into the details, but just to have that. What is the progress which we have been making? Of course, because of this air pollution, the number of air pollution stations which are there have been increasing under this National Ambient Monitoring Program, right? You know, it started with 7 stations in Agra and Anpara, and then since then it has been growing up. And this is where I would like to now bring in this particular link that, like, when you have these kind of a station, which was there in 1982, you cannot really stick to the same technologies which you were using in 1982 to really measure the same pollutant. And there are multiple reasons for that. And one of the two important reasons is that, of course, the concentration of the pollutant which you are increasing the time, you need to have sensitive of so time resolution and mission. Second and most important other reason is that there are multiple secondary pollutants which are now coming up, and various trace gases which we call them the trace gases because their concentration is extremely low. I did not really impact it on purpose, but know that oxygen, 21% oxygen, then you have these inert gases. And then these pollutants which we are talking about, they are really in a very small amount in the atmosphere. That's the reason of them trace gases, because they are really in a trace level. So that's the reason you have more secondary pollutants which are being formed, and then you really need to understand with them. So that's the reason, one of the reason that why do you always need the technological evolution, or why do you need a better and better technology to understand the air pollution? And that's what you need to, everybody needs to really understand, that the air pollution is not really the same as it used to be. Because, for example, air or probably soil pollution, you do not really get such a drastic change, probably for water, yes, but the pollution system as such is not really as done as it is in the air quality consideration as it is probably for the water and the soil pollution. So this is what it is, like, just to give you an idea that what it is, and then how do you really need to have this thing. And then what are the parameters they measure under the National Ambient Monitoring Program? And that's what I'm going to talk about, the monitoring techniques about, like criteria pollutants. I will stick to the techniques for PM10, SO2, NO2, and then I'll also try to talk about the well, there is a question. I think, can I take the question if the organizers can allow me to do that?
Yes, sir.
Dr.
So you can either
Yeah,
take it
so
now
I think
or you can take it at the end.
No, I think I always prefer to take the questions in between. And there was a question which was flashed on the screen, that what is
Yeah,
the
sure,
current
sir.
status of NMP? Was that the question?
Sir.
Ashwati, can somebody read a question for me? There was a question from someone.
Yes, sir.
Where can I see the question?
It's in the chat box, sir. So the question is, what is the current scenario of NAMP?
Yeah, okay. That's a very interesting question. And then the honest answer to that, I really do not know. But is the question in terms of that how many stations they have, or what is the technology they are using? So I'm not really aware in both the front. Neither I really know that how many stations they have, or what is that evolution that is happening. But what I know for sure is that they are really doing a good job in recent times, like, not only increasing number of stations, but even in enhancing their technology, right? I'm currently serving as a member of a national knowledge network program, which is a kind of a very sort of like very specialized advisory body to the Central Pollution Control Board. And then we have this regular meeting, and then they are probably doing a very fantastic job in all these things, right? They are going to completely revamp the air monitoring or air pollution monitoring technique in next this thing. I'll not go into the details of that, but they are also bringing in some kind of private agencies and then IITs and NITs. You would probably not see that in Kerala, because Kerala does not have, interestingly and nicely, Kerala does not have even a single non-attainment city, right? So if you want to be a part of that, you probably have to have a city which is kind of exceeding these standards, right? But that's not a good way of being the part of that team, right? So what you're doing is really good, and keep doing that. As of now, we do not have any what do you call so-called non-attainment city in Kerala at this moment, right? See that there are stations, but not for the reasons that you have any non-attainment city. Well, I hope that answered the question. If not, type it here. Right. Okay. What I'm going to do now is that I'm going to go into a little bit about getting into the techniques that why and what are the monitoring considerations which somebody has to take into an account, right? There are various this thing like see it's equally important along with the technology which we are using for the monitoring. It's not really that easy that we simply go and then set up a lab and then kind of start measuring there, right? There are various considerations which somebody has to really take into an account, and then that really starts from your objective of the monitoring, right? The first one is that whether somebody wants a long-term objective or if it is a long-term measurement or a short-term measurement, right? Now,
Sir, there is some problem with your audio, sir. You're not clearly audible. Your voice is breaking in
monitoring or
between.
audible, Ashvi? Yeah,
Uh,
issues and am I audible now?
yeah,
Am I
it's audible
audible
now, sir.
now? Yeah. So what
Yes, sir.
I would
Yes, sir.
suggest
Sir, it is still not audible now. There is some issue, sir, with the voice.
oh my God, what I have is it now audible? Hello?
Yes, sir. It is now audible, but at times
Uh,
it is breaking.
yeah, it breaks. Hello?
Um, there is, sir,
Can you hear me?
even now it is not very clear. Yes,
Just
sir.
give me a second. Just give me a second. Let me check what is the problem. Just give me a second,
Yeah.
please.
But now you're audible, sir. Now
Now
it
I'm
is
audible,
audible.
right?
Yeah, yes.
Okay, good. Yeah, so what I was trying to say is that there are certain monitoring considerations which we have to kind of take into an account, right? Manual versus automated, long-term versus short-term, polluted versus the background, so on and so forth, right? And then also generally the technique with which you monitor, of course, those have to be kind of approved and accredited by your pollution monitoring agency like the CPCB or the State Pollution Control Board. Monitoring of ambient ambient air pollutant, I would mostly probably be considering the SO2, NOx, CO, O3, so on and so forth. And then hydrocarbon probably I'll skip because I want to spend some time on VOCs and PM10 and PM2.5. I will probably, if the time permits, I will kind of talk about the sampling train and then what do I really mean by the isokinetic sampling. And then what are the factors which are associated with the quality assurance and quality control? And then what's the use of ambient air quality monitoring data? These are the things which, if the time permits, I would really try to go through further, right? All right. Now, again, to kind of deliberate and then discuss a little bit more about the sampling location, right? The limited number of fixed site monitors, which locations reflect the objectives of air quality monitoring program. So I'll try to tell you an example why this is extremely important. So I was looking into data with
बढ़िया
one of
क्वालिटी में
the
चल रही है ना
Indian.
वीडियो। सब लोग
Hello.
क्लास ले रहे हैं, बाहर के लोग हैं तो
Uh,
जाके नेट की सोच रहे जो नेट प्रयोग कर
someone's
लेंगे
mic
तो
is
ये आगे
not
चल
muted.
Hello. Can I continue, Ashwati?
Yes, sir. You can continue. Yes, sir.
Yeah. So I'll try to put an example, right, to know how the monitoring location or what your sampling objectives, whether short term or long term, why they are important. So one of the examples I would give you is that I was looking for a PM 2.5 data from one of such an agencies for a city where the PM 2.5 was really expected to the increase, right? And then I had that data probably from 2000, and then what is that? I don't know. Okay, something has popped up from my this thing. Okay. So I was looking into the data from year 2000 to 2012 for PM 2.5. And what I really realized when I was just looking into the trend of that data, what I noticed is that in year 2007 or year in 2008, the PM 2.5 drastically decreased from 9, and then it started increasing again. But overall values were much less than the year 2008. Like, let's say up to 2008, it was, let's say, an annual average was, let's say, 60 microgram per meter cube. In 2009, it came to like 35 microgram per meter cube, and then started increasing again. Now, when I looked into this, my mind told me that this data particularly belonged to a city where it was not possible. That city cannot really have such a drastic reduction in PM 2.5, which came from 60 to 30 per meter cube. Now, when I went and then somebody has raised the hand for a question, maybe, I don't know. Should we take that question up? Okay, I think they should just type. So I knew that it's not possible. So when I went to the agency to kind of understand more what was happening there, interestingly, what agency told me that the station which they were kind of referring to, the representation of an urban location, they kind of moved it from there to somewhere which was a little bit of a more of a background and not really the traffic junction or so something, right? So you cannot really do that, because then your total scientific objective is screwed up. And they said that, well, why they had to do it? Well, they said that this place which was belonging to someone, lease was over, and all that reason. Well, of course, there could be reasons behind this. But then these kind of the things which somebody has to already take an account in addition to the technology which you are going to use. Anyway, and then there are obviously you have that what is your lower limit of detection. One classic example in India, where do we really go wrong as far as the lower limit of the detection is concerned, is the sulfur dioxide. So majority of the instrument which we get in India based on the UV photometric technique, the SO2 concentration in India is much lower for the advisable technique, right? So you have to take those things into the account. And the most important is that if you are using an offline instrument, then how the collection efficiency, your flow, and so on and so forth are important. I'll also try to give you an example. Like we do have a laboratory in Munnar at a high altitude laboratory, right? So when we go and do the measurement, the first thing you have to understand that all our pumps and flows needs to be recalibrated. When we use the measurement or do the measurements in Chennai at IIT Madras, we are dealing with this at the level of the sea level pressure, that is 1015 hectopascal. But when you go to the Munnar, being a high altitude site, it is 835 hectopascal. So all our pumps and all our flows and everything needs to be calibrated. So these are the things which you have to really understand. Okay, once you have understood what your objective is, what your frame is, or the reference, try to have and understand what are the differences which are used for various techniques, which I am kind of going to understand it today. SO2 is a spectrophotometry that's also used for the ozone, but it can also be monitored using chemiluminescence. I will about the ozone measurement only through the what you call UV photometry and not through the chemiluminescence. If time permits, I will do that. Then nitrogen dioxide, of course, is the gas phase chemiluminescence. That's the technique which they use. And then that's a pretty reliable technique, but it has certain disadvantages. And then I'll try to talk about those disadvantages, why you need to consider about those. Then you have CO and CO2. So I'm not really talking about the CO2 because they use the same technique called the non-dispersive infrared photometry. Then you have the non-methane hydrocarbons, which they use the gas chromatography, which is called as the flame ionization detection. It's a pretty old technique, but I would probably skip that simply because I'm going to talk about the VOC measurements using the PTRM. And then obviously you have a PM10 and PM2.5, which is again an offline line, because once you are talking about the offline measurements, it is 10 PM2.5. But we talk about the very advanced equipment. That's not essentially the aerosol measure. That's what I'm kind of going to talk about, the online measurements for them as an aerosol measure. Let's get started with these techniques. We will kind of run through these techniques because one not the same thing is same technique which they use. Now,
Excuse me, sir.
the fluorescence is within, yeah.
So, like before going into these details,
Yeah.
can we look into the questions in the chat box, because some of the questions that are related
Yes,
to like some of the previous things that I heard.
Sure, please do so.
So,
We can take the
one
questions here,
person
no
has
problem.
asked.
Sure.
Yeah, okay, sir. So I'll read out the question, sir. So one is, before to start the real-time experiment research work, what are the special features and factors to be studied before the work?
Yeah, right. Okay. So the question is, if I understand correctly, that before you are doing into the real-time and online measurements, what is that you have to consider, right?
Yes, sir.
Yeah, okay. So the first thing which I really said is that, like, what are your consideration? So one is that whether you are going to do the routine monitoring, like, whether you just want to have a routine monitoring of the criteria pollutant for the long basis. Are you just going to see that how their seasonal variation is, or how they are going to increase over the next 10 years or so, right? That's one of the considerations which you have to do there. So the first thing is that whether it is a routine monitoring of the pollutants, so that you want to know that whether pollutants in your area are exceeding standards or not. That's the very first monitoring, to check that air quality you are reaching given standards or not. That's the thing. Then the second thing, which basically comes and becomes a little more scientific, is that obviously you would like to draw some more scientific conclusions from it. Let's say, for example, you want to see that, like, ozone being a secondary pollutant, right? Whether ozone has a seasonal variability, why that seasonal variability is happening, right? That's basically an additional thing. What happens into that, like, whether you want to do the routine monitoring, then the objectives and then the maintenance and all the aspect or complete become very different. Whether you want to know about those pollutants, then your flowchart to perform these measurements is again different. So depend that what your objective of the work is. Let's say, for example, the CPCB monitoring stations. So the CPCB monitoring station, their objective is really a top quality air quality monitoring, right? They do not really go into the details behind it. Like, you would see a CPCB into the how your ISO, whether your team open region is limited. CPCB does not do that, right? Because that's not in their purview. So you will have to derive your objective in that way, what exactly you want to do, a routine or research. Actually, I hope they answered the question. Maybe take the second question then.
Yes, sir. And there is a question. There are data available in internet related to air pollution. Are they the outcomes of NAM?
Yes. So I think the city, they have routine monitoring at the metro city, but I think the non-metro cities, whatever the data which is available, it is the outcome of the national ambient. Data is really freely available. It is relatively nicely quality checked. But as I said that, like, they have their objective is really to perform the routine and regular monitoring, right? So if you wish to go into the detailed science behind that data, using that data, it's better that you with them that what is the scientific conclusions which you would like from it. Is there any more questions for you?
Yeah, there is one more, sir. Like whether carbon footprint can be assessed in air quality.
That who is emitting more carbon? Well, no. I mean, the carbon footprint probably cannot be added into the air quality because the carbon footprint is something that, like, it can range from how much carbon footprint I am emitting to particularly an industry, right? So how would you differentiate and tag a person or tag a process or tag an activity that who is kind of really doing how much this thing carbon footprint are. But yes, using the carbon dioxide data, some sort of an emission data from the various sector or various activities, probably you could really go and then calculate that how much carbon footprint is being uh, tracked from the different activities or the processes. That's possible, but not as in terms of the air quality. There are more questions?
Okay, sir. So there is one question on isokinetic sampling, but I hope that you will be coming into it.
Yes. I'll come to the isokinetic sampling. If the time permits, I'll
okay.
come to the isokinetic sampling, but I will make sure that I will answer that question. Like even if I do not get time to cover that, but I'll definitely make sure to answer that question.
Okay, sir.
So may I move ahead now then?
Yes, sir. Sure, sir.
Okay. All right. So then we were basically going to talk about the different measurement techniques, right? So let's try to talk about the sulfur dioxide measurement technique. Now this is again really based on the UV fluorescence. So of course you might have generally through your school or colleges sometimes you have really heard the word called spectroscopy, right? Or the spectrometer. Now, what I really want you to do, I will not go into the basic fundamental physics behind it, but I'll try to very quickly explain what do we mean by that. Well, if you look into the any spectrum, like, let's say, for example, electromagnetic spectrum, where you have the very high wavelength or low frequency radio waves to you have really gamma, alpha, beta, gamma rays, right? We have a very high frequency. And then there is one very small portion of that electromagnetic spectrum is the visible UV, infrared, or near infrared, right? So this is really very important as far as the atmospheric gases are concerned. So what it basically means is that, like, if I have the energy band or the vibrational energy between two molecules matching with the frequency of that particular spectrum, that the energy which is associated with that frequency of the spectrum can be absorbed or can exactly matches with the band gap of these particular molecules. So I'll try to give you in a very simple example in this case. Let's just I believe that all of us in some point in our life we would have tried to kind of push our friend on a swing, like friend or whoever is sitting on the swing, and then you kind of try to push that swing, right? Now when you are pushing that swing, you have to be very nicely synchronized with the swing, right? You have your energy, you kind of raise your hand and then really push it, right? Now you imagine, so then only it is possible that can swing can get the energy. So then only it is possible that you can easily transfer the energy in your body to that swing. Now, if it is not really matching with that particular process, either you will be down on the ground or your friend will be down on the ground, right? So you can try to understand this quantum mechanical behavior of the molecules about the energy absorption in this way, right? So these molecules, they vibrate in a different direction, and then they really kind of absorb the energy in that particular wavelength. So same thing basically happens here. So when I talk about the SO2, so what they basically do, that we know that the sulfur dioxide can basically absorb in probably some of the wavelength. I don't recall. I think I should have. I think it is probably 200 to 240 nanometers. I think I should have written it here, but I have not written. It is probably 200 to 240 nanometers. It's something where it absorbs. which is in a UV range. So it absorbs into this range. So what basically means is that if you have the light source of this particular wavelength, right, so what will happen is that this SO2 will absorb that energy. And now you know that, of course, from very beginning, we know that if it absorbs the energy as a very basic behavior of that molecule, right? It will go into the excited state. But once it goes to the excited state, it will always come back to its original state, right? When it goes into this excited state, it is basically denoted by this SO2 star. But this SO2 star, when it kind of comes back to its original state, that which happens of an excited SO2 molecule, it basically emits a characteristic radiation, right? It will radiate that energy in some or other form, right? Now, what they basically do is that you have your source in here, your gas sample basically comes in from here. Now, depending upon how much SO2 you have, whatever the UV radiation which you are giving in here, that absorption will be more. If you have no SO2, you will have no absorption. And then you basically get the sample out here. But then what happens is that you have these radiations which are coming out through of an optical band, which they have something like a photomultiplier tube, which does nothing but kind of converts a type of a signal to the electrical voltage and current, obviously, and then you kind of convert that current and voltage to an electronic, and then it basically goes to some sort of digital to analog, analog to digital converter, blah, blah, blah. And then it basically gives you the concentration outside there. Now, this process, which I told you it's probably an oversimplification of what I was talking about, but I want you to understand the basic science behind this is that it is a very typical spectroscopy related with that. Now, what basically happens is that this particular thing would depend on what concentration you really have in here, right? If you have really high for the SO2 analysis is not as one would expect at the low concentration. Power continuing would really work. But if you put it right back of your nice clean atmosphere outside your house, probably you would really see a very little variation as far as the SO2 is concerned. The most important one is the gas phase chemiluminescence technique, which is really used for the measurement of one of the most important gaseous pollutant, that is nitrogen dioxide. That is something which is called as the oxides of nitrogen together, what it is called, like, that's what is basically measured through this one, right? So the way it is measured is very interesting. So what happens is that in the atmosphere, when either you emit the NO and then you emit the NO2, and then together they are basically called as the NOx, that is the oxides of nitrogen. Now, the formal definition of chemiluminescence is the emission of a light from electronically excited chemical species, which is formed in the chemical reaction. So it is slightly similar to that. Here, your gas is directly absorbing that energy. You are not happening any reaction. The reaction itself is happening between SO2, your gas molecule, and then the energy which is available. But here what you are doing is that you are making some reaction happen, and then basically some sort of a light or electronically excited chemical species is formed in a chemical reaction. Now, the interesting part is that this NO is basically emitted from the vehicular activities or any other regular active combustion activities, which, just give me a second, let me have some water, please, excuse me. Sorry. So now what we know from the ozone chemistry is that one of the fastest reaction of NO is with ozone. So what it means that if this NO, which is emitted in the atmosphere, before it reacts with anything else, it goes on to react with ozone. And then when it reacts with ozone, what it basically does is that the first thing which it forms is an NO2 molecule, which is in electronically excited state, and plus the oxygen molecule. Now this ozone, this NO2, which is in an excited state, when it comes to its original state of NO2, like, when it comes down to its original state, it basically gives the H nu. Again, it gives some energy. So what they basically do is that they have this reaction chamber where you kind of sample your NO2, or when whatever your sample is from the ambient measurements, and then you kind of put an ozone generator, like you can simply generate the ozone by a simple machine, that you take your ambient sample and pass it over through a UV light, it gets converted to the ozone, and then they kind of put some sort of an known amount of ozone here, particularly when your sample is drawn. Now, when your sample is drawn, it will definitely have an NO molecule in that. It will react with ozone, which is there. It gives you NO2. Now, understand that the signal which is being generated by this PMT tube, that is a photomultiplier tube, it will be directly, that signal will be directly proportional to the amount of NO which is available in the atmosphere, right? More the amount of NO, it will react more with NO ozone, and then higher this signal will be. So this signal is directly proportional to the amount of NO which is available, and then you have this PMT, obviously, and then you kind of go and then kind of do that, right? Now this you basically measured NO. How about NO2? Because you basically want to measure the NOx, which is basically nothing but NO plus NO2, right? So now what I told you is the only the measurement of NO, but not NO2. Now what they do is that they take this NO2 sample, and then by using some sort of a very simple technique, this NO2 they convert it to NO, because you know that only NO can react with ozone, not NO2. So they kind of convert that NO2 to NO, and then again the subsequent reaction, which kind of once you have converted, it goes back to this reaction, and then the cycle can continue. Now here is the tricky part as far as this technique is concerned. So please concentrate here for 2 minutes. So how do they convert that this NO2 to NO? Is that they take this molybdenum material. Molybdenum is a material which is available. They hit this molybdenum, I think probably, if I'm not wrong, up to 600 degrees centigrade. What this basically does is that NO2, when you pass it over the molybdenum at 600 degrees centigrade, this is what the reaction which you get. Now you have successfully converted the NO2 which is present there in the atmosphere to NO, and then it can again go back to this particular cycle. So what they do is that they probably put some sort of some kind of a valve here, right? Some sort of a mechanism here, that once your sample basically coming in, it's coming in directly from the atmosphere. Then the other sample is basically kind of, they put a solenoid valve here. Then one sample basically comes from directly from the atmosphere. The other one directly comes from the not directly, but then converted from the molybdenum, and then it goes to the same reaction. So in cycle number 1, it is your NO, and in cycle number 2, your signal is directly proportional to NO2. And then when you add basically these two signals, what you really get is oxides of nitrogen. But there is a very small caveat with this technique, is that please understand that when you pass an ambient gas over the molybdenum, it is not only NO2, but there are certain other chemical species or the constituents present in the atmosphere, for example, PAH or PANs, those also can get converted into NO. So that is the reason in an urban region where you have a lot of these other pollutants, when you are reporting the NOx measurements from your chemiluminescence techniques, those could be the lower limit of basically what you really observe in the atmosphere. And this is where this question which was there, that whether you want to use it just for a typical monitoring purpose, whether any pollutant is exceeding your standard or not, or whether you'd want to draw certain type of a very specific scientific conclusion is important. So it is very important to understand that using this technique, you cannot really draw onto very strong scientific conclusions because it's not only NO2, but there are other species present in the atmosphere which can also get converted to NO. All right. Now let's go into the other one, which is extremely important, either CO or kind of CO2. Uh, this particular technique is called as a non-dispersive infrared spectrometry. Like as we talked about the UV spectrometry, this basically talks about the infrared spectrometry. So as you might have guessed rightly now, that since the SO2 was absorbing into the UV region, the CO or CO2 basically absorbs into the infrared region. And then you know that the CO, considering if you look into its energy bandwidth, and all that stuff, that the CO kind of so for a SO2, when you want to swing that cattle, you have to really push it hard, right? So probably there is a high weight. But if a small child is kind of sitting, you have to push that swing with a little bit of force, not very high force. So same thing is there, that CO strongly absorbs infrared energy at the infrared wavelengths. What is the detection device? The detection device is a very complicated one as compared to the SO2, which has a two cylindrical cell, a sample and a reference cell, meaning that in a reference cell, you probably have a known amount of CO, right? You already know the CO concentration here, right? So let's say certain X ppm or Y ppm, whatever it could be. And how do they do it? Like they use the palladium pallet, like you put the palladium pallet and you know this thing. So what it basically does is that it has a two cylindrical cells, a sample cell, and this is where your sample comes in. And then the difference in the infrared energy is in the two cell is the CO concentration. So you basically kind of draw in your sample here, right? And then obviously you know whatever the concentration you have here. And then when you kind of put your sample here, obviously you are adding some more CO here from the atmosphere. And then when you try to subtract this, because you already know what your concentration is here, the difference in that signal is basically nothing but your CO concentration. It's not really that difficult, but again, this is really a very oversimplified version of what electronic or what the details they go into. Depending upon the requirement, that how sensitive instrument or how much your concentration is, if you are really looking into a very high concentration CO, where obviously your concentration is high and then the cell is very sensitive, it can work. But there are various different design concentration or the design consideration for an analyzer which kind of define the sensitivity of your instrument. That is the reason when you are purchasing your instrument, please try to look out for the resolution which it works for, the time resolution, the concentration resolution, and also the sensitivity. That is the reason you can also buy a CO monitoring probe for 25,000 rupees. And then you can also have a CO analyzer, which can cost you like 6 lakh rupees. And that's basically comes from this fact that how do they define or how do they further design the electronics after this as far as the sensitivity is concerned. Let's go to the ozone further. It is on the article photometry and chemiluminescence. Chemiluminescence is it's something which I'm kind of going to skip it here because that's not really being used so widely nowadays. As I have told you that just like the SO2, which probably I said like, did I say it like 200 to 240? I believe, yeah, probably. But the UV, the ozone has a very strong absorption at 254 nanometer. And then the very classic example of this is that the ozone which is sitting in the stratosphere right above your head beyond 12 kilometers is good ozone, because that is the reason, because it absorbs the all incoming ultraviolet radiation from the sun, and it protects the earth's it's protecting us from the UV light directly coming in. And that's what I said, that's what exactly the finding which Professor Paul Crutzen has done, that they have found out the reason that why the ozone is destructing. So had it not been to Professor Paul Crutzen to find that, like, well, probably some of us would have already been started suffering from the skin cancer. Anyway, that's the second thing. So what basically they do is that it is again a little bit of an oversimplification of it. So what do they have is that along with this is that they kind of have some sort of a reference cell, meaning that it kind of passes the air without the ozone. So right, so they will install some sort of an ozone scrubber here. So no, not here, sorry, I think I made a mistake. It should not be here, right? So it's not here. So what they basically do is that you have a sample which is coming in here, and then you have something which is called as an ozone scrubber, like it is called as ozone scrubber. So ozone scrubber means that they will remove that ozone from your sample, and then they kind of they will have a UV light again in here, and then it goes to the detector. So why do they basically do is that there could be some other gases as well which also kind of absorb at 250 nanometer. I leave it to you for think. Maybe you, when you go home after this lecture, try to find out which are the other gases which can also absorb at around 250 nanometers in the atmosphere or around that range. So what happens is now you have your ambient sample coming in from somewhere, right? You have your ambient. This is the this is not the sample. This is the UV light. So so I will kind of say that this is the sample. Yours, I kind of this is the sample, and then you have an UV light, and then the detector inside, like we can say that this is an UV light coming in. So you have a sample coming in. Now, whatever the absorption which has happened because of your ambient sample is now detected by that detector, and then say it is an X voltage. You have analog to digital converter from the PMT, blah, blah, blah. It goes in. Your ozone is now removed here, right? And then it kind of goes in, like again, you have UV light. So now whatever the sample which you have, like if your signal is now Y, you know that the difference between these two, what you get is a signal which corresponds to your UV, corresponds to your ozone concentration. This technique is very effective because over the period of time, it is pretty straightforward because there are, at least at the surface level, there are not many gases which can absorb at 254 nanometer. And then with the improved electronics and improved computer techniques and other things, this technique has really become very popular as far as the ozone monitoring is concerned using the UV photometry. So wherever you go, the instrument which you see around is the UV photometric analysis. Ashwati, I would come back to the PTRMS at a later time, but do you want to take few more questions here before I go on to the particulate matter? Dr. Ashwati? Am I audible to someone? Somebody can confirm that?
Yes, sir. Audible only, sir.
Okay, I'm audible. So maybe Dr. Ashwati is not here. Okay, that's fine. But is any of the host is there so that they can help me with the questions, maybe?
Sir, I'm back. I just got a call in between.
Yeah, sure. No problem. Please do so. So what I was thinking is that maybe, so I will come back to the PTRMS and AMS at the last moment, but should we take maybe a few more questions here before I move on to particulate matter?
Yeah, sure, sir.
Sure,
But some of the questions, they are related to PM actually. So
okay.
the first question
Sure.
is, what is the difference between soot and PM? How the concentration of soot can be measured?
Okay.
And there is one more question that is on what are the reasons behind smog formation very often in Delhi? So these are the two questions. So maybe I think once you talk about the particulate matter, these things.
Maybe I will take the suit question because the respected audience one of the members of the respected audience who asked this question will probably better understand the particulate matter measurement then. So
Yeah, sure.
the suit itself is called as a particulate matter because the moment it is kind of flying around in the air, and then once it sits in it, so soot, mineral dust, sea salt, then pollen grains, fungal spores. All these are particulate matter, right? The soot is one of the specific type of particulate matter, or sulfate particle is of specific type of particulate matter. So soot itself is a particulate matter. As far as the soot measurement is concerned, there are various techniques, either optical or thermal, right? Which I'm not going to go into the details of that, unfortunately, because of the time constraint, but maybe that could be for some other coursework or so, something which one can look into this one, right? I hope that answered the question, basically. So soot itself is a particulate matter, just like any other particulate matter. All right. The other question, which is
Other
kind of
question
like
is
the
it's
fog
on the
formation in
smog
Delhi.
formation.
Yeah, well, I mean, we have done a very extensive research about the smoke formation in Delhi, and then recently published a very highlight paper in Nature Geoscience about it. It's very complex, right? It's not that easily I can explain you, particularly the smoke formation over Delhi. And this is a very classic example which I say that how the evolution is evolving, right? When you talk about the London smog, or when you talk about the Los Angeles smog, that was mostly the ozone was the primary uh, component of it. But when you talk about the Delhi fog, or smog, really speaking, it's not fog, it's a smog. It's very complicated. So what I would request that a person who had that question maybe stay back after some time, and then I'll try to explain in a very simple language that what basically happens. Is that okay, Ashwati?
Yes, sir.
Okay, thank you. So if there are no more questions, let's go on and move about the measurement of particulate matter.
So there is one more
Yeah,
question now.
yeah, please go ahead. Please go ahead.
If carbon monoxide is not a greenhouse gas, how it absorb infrared wavelength?
How it basically?
If carbon monoxide is not a greenhouse gas, how does it absorb infrared wavelength?
Well, that's a very interesting question. When you look into the what do you call look into the spectrum, right? It has a certain range, right? And what happens is that it is not essentially true that the carbon monoxide is not a greenhouse gas, right? It is a very weak greenhouse gas, right? So something which is a greenhouse gas is not completely kind of defined by what it absorbs, but also whether what it emits, right? So let's say, for example, tropospheric ozone, for that matter, right? It doesn't. So the greenhouse gas is basically defined by something which emits into the infrared region, right? Because the infrared region is something which really hits your atmosphere, right? So absorption, for example, is not really what you really call, like, for example, tropospheric ozone. It is a greenhouse gas, right? Depending upon the what it really emits. So it is not necessarily. I mean, that's a kind of an very gray information that a carbon monoxide is not a greenhouse gas. It's kind of a very weak greenhouse gas, because not that it absorbs into the infrared region, but what it emits is not going to cause the hitting of the atmosphere, right? That's the reason it is that. So carbon monoxide, basically, you can call it as an indirect greenhouse gas, because it reacts with the OH radical and then gives rise to the different gases, which are the greenhouse gases. I think that probably answered the question. Is there any more question?
Yes, sir. There is a question. Generation of ozone being too costlier, how economical would it be for measurement?
Well, I mean, the generation is very costly, or I missed your word in between. Can you please repeat the question?
It is generation of ozone being too costlier, how economical would be for measurement?
Well, I think it's probably over the period of time, the measurement has really measurement is really being becoming cheaper and cheaper, right? And then if it is not cheaper and cheaper, at least the quality of the, or the sensitivity of the instrument have been really increasing, right? Now, of course, that's an interesting part which somebody mentioned, that why the ozone generator is important. Well, I mean, it is expensive simply because when you want to put that for a chemiluminescence measurement, it is very you need to have a very accurate concentration of ozone which is going into your chamber where you want to measure the NO2. But a very simple thing which I say, let's say your typical uh, water filter at home, like any company, so they have an UV lamp in that, right? So when you pass a water through it, probably it's just a very simple thing, you want to kill those bacteria, right? Or if you can just hold a UV light outside your house, well, I mean, if an oxygen is passing through it, like some of it is definitely getting converted to the ozone. I would recommend the respected audience who asked this question to simply look into the Chapman mechanism, right? You know, you have ozone, which is broken by the UV. You have again an excited oxygen molecule, which again reacts with oxygen and then gives rise to the ozone molecule again, right? So it would depend, right? You know, so yes, but depending upon your application, why do you want to generate the ozone? It could be very expensive as well. Yeah. Next question, Ashwati, if any.
Yes, sir, there is a question. Is it right? Need any catalyst in transformation of SO2 to SO3 pollutants?
Is there any?
Is it right? Need any catalyst in transformation of SO2 to SO3?
Whether we need any catalyst while transferring from SO2 to SO3, is that the question, if I understood correctly?
Yes, sir. Yes, sir.
Probably not. I don't know if I got the question correctly. I would request the respected member of the audience to stay back and then I can discuss it after that. Is that okay?
Yes, sir.
Okay. Next question, if any.
Sir, there is two more questions. Is there any possibility to change environment condition by natural cyclones?
Oh, interesting. By natural cycle, if it is possible to natural cyclones.
Yes, yes, sir.
Well, momentarily, yes, of course. I mean, it does change momentarily, but in whether it leaves any sort of a permanent effect on the environment in some or other region, I don't know. I'll have to look into this one. Probably I'll have to discuss it with the member again. Yeah.
The next question is, can a non-dispersive infrared spectrometer NDIR can be used for carbon monoxide measurement?
I think yes.
That's all, sir.
Yeah.
These are the questions.
That's all. Okay. Okay. Very nice. So we can go ahead then now. Okay.
Yes,
so I don't know. I'm getting this annotation request. I'm getting like somebody's is requesting to annotate the shared content. What should I say? Decline or approve?
Sir, you can decline and you can go ahead.
Can I decline that?
Yeah, yes, sir. Yes. Please decline.
Okay. Okay. Thank you. Thank you. Okay. So I think it is very important for me to make a distinction here is that why the aerosol, what is the basic difference between aerosol and a particulate matter? And then when do you care about particulate matter and when do you care about aerosol, for example? Well, by definition, an aerosol is a collection of suspended particles, either solid, liquid, or aqueous, and the surrounding gases, like, any medium. And for our case, it is atmosphere, right? So it is surrounded in nitrogen, oxygen, and then other inert gases. That's an aerosol. A particulate matter, for example, which is more commonly referred as to when we talk about it just to the suspended solid or liquid matter, right? So once you collect that particle, once you are kind of pinpointing that particle, when it is not governed by any of the laws, like Stokes law and gravitational force and buoyant force and all that stuff, it is not governed. It's something called as a particulate matter because you are collecting it on a filter paper to do some sort of an analysis further. Now, what happens is that the particulate matter is a definition which is more used when you are trying to understand the health effect of the particulate matter. And uh, is there any question or so something? Should I stop or should I wait? Like somebody wants to say something? Hello?
No, sir, you can continue, sir. There is no questions.
Because, okay, I heard some disturbance. So, okay. Oops, I hear it again. Okay. And then so depending upon what your requirement is. So generally, when you talk about the particulate matter, that term is more like you might have heard the term called PM 2.5, which means nothing but the particulate matter where the aerodynamic diameter of the particles is less than or equal to 2.5 micron. That's the this thing. But when it comes to, so generally the term particulate matter is mostly associated with the health aspect, and then the aerosol is mostly associated with the climate aspect. What I'm going to do is that, like, I will just try to make you understand, appreciate this fact that why the aerosol measurements is much more difficult than the gas phase measurement. Now, what happens is that anything which is less than one nanometer is a gas molecule, right? So you don't really need to worry about it. But if you look into the aerosol, for example, it basically starts from 1 nanometer and then can go up to almost 100 micron, right? So when you are talking about like sulfate particle, secondary organic aerosol, soot particle, mineral dust, sea spray, the proteins, the viruses, the bacteria, the fungal spores, the pollens, right? You really have almost like 6 order of magnitude diameter which you have to really consider. So you cannot have a technique which measures only from 1 nanometer to 10 nanometer and then draw the conclusions for the particles which are in this size range. You cannot do that, right? And that is where the particulate matter measurements or the aerosol measurements become tricky, difficult, and more expensive. That's the reason the any instrument which, or particularly the online and real time, which you go on to purchase, is at least 10 to 20 times expensive than any gas phase measurement. Because in gas phase measurement, you are not dealing with the size, but you have an optical bench inside your instrument where certain reactions are happening and then you are done. But here it is not the case. You are dealing with like 6 order of magnitude difference for the particle size. That's basically important. I'll skip this thing. I'm also going to skip this, right? Okay. Now, where does the PM originate from? Like, you have obviously the primary sources, as I have talked about, like it kind of goes, something goes into the atmosphere from various sources. But the another important factor which we always neglect is that the particulate matter can also be secondarily formed in the atmosphere. Depending upon the situation, location, and in the primary pollutant which are emitted in the atmosphere, in some cases, the contribution of the secondary organic particulate matter or a secondary particulate matter can even exceed the mass burden of the particulate matter. And what is an impact it can have? I mean, of course, it can have a huge climate and health impact. But one of these things is this thing. You can see on this photo that here how your visibility is very nice and high visibility, and how the poor visibility is in this particular case. And that's what exactly is happening in Delhi, where we have now found out what could be the potential reason from that. The primary sources, I will not go into the details of that. You might have taken these various courses about stationary source, mobile source, line source, point source, so on and so forth. But these are broadly the various sources which you can talk about as far as the PM is concerned. What are the factors which decide the concentration of the PM in the atmosphere? And you need to really consider these, because when you are applying any sort of a measurement technique, you would need to know that what are the conditions which define the PM concentration, obviously, which will really help you to choose the right set of instrument as far as is concerned. So these are the different, I mean, majority of these do also affect the gas phase measurements, but I did not bring it when I was talking about the gas phase measurement, because they will not have as much impact as it has on a PM measurement. as compared to the gas phase. So you need to be careful about the weather patterns, wind, stability, turbulence, precipitation, rainfall, so on and so forth, right? Smokestack height and so on and so forth, obviously, is very important. I'm not going to go into the very importantly, how it really affects the human health. Well, depending upon the size of these particles, they can go and then sit in your respiratory system. And that is what we are really talking about, the corona particle, the coronavirus, that what is its size. And then now people are saying that it is kind of piggy banking in some of the aerosol particle and then kind of going in your alveoli, so on and so forth. The very critical effect of the particulate matter is, and then if some of these particles, those can reach the lungs, if they are toxic, and then they can kind of get exchanged into the blood system, and then can put that toxic material into the blood system. Extremely dangerous. Not going to go into the details of this because that's not really required. That of course it does have like a lot of effect. And then what are the techniques which are really used for that one? This is what something which kind of tries to tell you that what we really need. As I have really talked about in the beginning, the very important aspect is about the concentration and size distribution. When you talk about the PM 2.5, it's mostly the size distribution. Is Dr. Ashwati there? Can you please try to tell me how much time I still have so that I will kind of arrange it accordingly?
So you can take another 15 to 20 minutes. Huh?
Another 20 minutes, right? Okay.
And so,
and then after
maybe
that,
like,
I can still have the question.
Yeah, sure, sir. Actually, sir, even if you don't go into details of these instruments also, it's fine because we have another session coming up on the specifically for the PM measurement instruments.
Oh, very good. Very good. So I think I can then skip the PM and then maybe just talk about the online ones.
Yes, sir.
Okay, that's fine. Okay, so thank you very much for that information. So obviously you have two things. One is the concentration measurements, where you directly come to know that how much mass of the particulate matter is there in per meter cube of air which you have sampled. And then the other one, which is most important for the climate perspective, is the size distribution. And this is what I would then talk, because now Dr. Ashwati just told me that there is another session on the PM measurement. So these are the different instruments which can give you the various only concentration, which is kind of filter, impactor, and then obesity meter, and then I don't know, various technique, like, and then all these filters basically and impactors, they use the gravimetric method, which another respected speaker will talk about. But when you talk about the size distribution, then you obviously have the microscopy, you have the impactor, it can still be used. I'll quickly run through that. Then you have the diffusion kind of a battery. You have a DMA, which is called as a differential mobility analyzer, one of the very widely used and most expensive instrument. And then in combination of the SMPS, the DMA, and then some other instrument which can count the particle size, the particle number, it's called as a scanning mobility particle sizer, so on and so forth. I'll simply, so this somebody is going to talk about the PM measurement. So I will for now then skip this one, because the cyclone separator is one of the. Hello.
Sir, it seems it's from the participant side, like someone has
Okay, I will neglect it, sorry. Yeah, sure, no problem. So if somebody is going to talk about the PM measurement, so then they will cover the PM impaction, and then all that stuff I'm then going to cover. Very nice. That saves a lot of my time. Thank you, Ashwati, for that. This saves my time, this impactor and other thing. Then I'll skip this. Yeah, then I kind of will quickly go through these online measurements. Okay, so one of the very important instrument in the aerosol science is called as the something like which is called as the condensation particle sizer, or the also another one is the aerodynamic particle sizer, or an APS. So let's try to understand this CPC, which is called as the condensation particle counter, and how does it basically works, for example. So CPC, what basically happens is that, I mean, this is something which is a very complicated design, which I would not go into this one. So you basically kind of get your aerosol particle, And then once your aerosol particle comes in, you kind of have some sort of a bath, which is kind of filled in with the butanol. And then you kind of have some sort of a saturator or some sort of a mechanism here that this butanol is kept at like 36 degrees centigrade. And then you know that the butanol is very volatile. So you will have these vapors going on from the butanol. Now what happens is that whatever the particle which are coming in, this butanol vapor will condense on these particles. Because of this condensation of the butanol on these particles, this particle will grow big enough. These particles will grow big enough. These particles are basically subject some sort. You have these lasers, two laser source. Let's say this is your laser source. You have two laser source, which is generally separated by the distance of 100 micron. It is simple. Its wavelength could be, I don't know, maybe like 420 nanometer or so something. Now, what happens is that this laser will simply count, not even one. No, sorry, this is for two. You have one laser, and what happens is that once the particle passes this laser, it counts it. So it basically generates this kind of a pulse. It keeps every time the particle is passing this laser, it is kind of generating this pulse. So you know one particle, two particle, three particle. Then you are pulling the air through this particular instrument with a known flow. So if you know the amount of volume you are sampling in a given time, then you also can calculate the concentration based on that. Now, the obvious question which somebody may ask, like, why do you need this kind of an arrangement here? Well, whatever the particles which are coming in need to be bigger than the wavelength of the laser. If your laser has a 600 nanometer wavelength, then any particle which is less than 600 nanometer will not be detected by that laser because that laser will not see it. And this is the most effective and very quick way of growing the particle by condensation. And then, of course, this laser will keep counting it, and then you basically know how many particles you have in a centimeter cube. But that's not really dependent on the size, but it will simply count the particle, that how many particles you basically have in there. This is an optical particle counter, right? It doesn't, again, the same thing, like, but only for the bigger ones, like, you have a big particles, like you kind of carry these particles through some sort of a laser here, like, once the particle comes in here, it kind of like it's a sample cavity, only one particle goes at a time. Oops, sorry. Goes in here, and then this detector detects that whether a particle has passed in or not, and then you obviously count that particle. That's the simplified version after the condensation. This is the condensation particle counter, the complete view of this. So you have your sample inlet. The sample inlet basically goes in from here, and then you have a liquid soak felt or this liquid pool where you use the butanol, which is here at 37 degrees centigrade. And then you kind of, when the particle is going here, you have some sort of a condenser where you suddenly cool that particle to 10 degrees centigrade. So what happens is from 37 to 10, it comes very quickly. The condensation is very effective. And then the moment that the condensation has occurred, then you have some sort of an, the counting here, basically, which is kind of an heated optics, which will not hit the particle. And then there is a filter, and then the particle basically goes out. That's what the complete assembly of the condensation particle counter. There is another interesting instrument which is called as the time of flight particle measurement. So what basically it can really provide you the real-time high resolution size measurement, but it requires a very important aspect is the calibration. So what it basically does is the following. So it basically kind of an aerosol particle is sucked in through this very narrow this thing. And then you have something which is called as a narrow beam range here, which is called as an aerodynamic range. So what it basically does is that it basically push all the particle with the same acceleration. The pushing of the particle is not changed. So if you push the bigger particle with the same acceleration, as compared to the smaller particle, obviously the smaller particle will move faster than the bigger particle. Now, what happens is there are these two laser beams, the lead laser beams, which are kind of separated by the 100 micron distance, 100 micrometer distance. And then what happens is that once a particle is pushed through this one, you basically calculate the amount of time which is basically being taken from this laser to this laser. And then you kind of calibrate this instrument, putting the amount of particles through the same acceleration. And then obviously you have a very sophisticated electronics, which will try to tell you that if a particle took this much time to travel, it means that it falls into the size bin of like 30, it falls into the size bin of, let's say, 600 nanometer to 700 nanometer, or 600 nanometer to 610, 610 to 620. Again, the problem is that you cannot go to the smaller size than your laser wavelength, because your laser does not really see the size. And then again, simply this counting goes on, and then once the counting goes on, you get a size distribution, but that size distribution is really higher than what you basically said. Very quickly in another 5 minutes, I'll combine this very effective technique, which is the one to kind of to understand. It's an expensive instrument called scanning mobility particle sizer, which includes the technique of electrical mobility. It is basically capable of measuring the size distribution and concentration of the particle, which can vary from as well, I think I would say that 2 nanometers to up to 1000 nanometers. It's extremely effective instruments. And then it really required to understand the climate studies, right? It is very complicated, but it kind of takes the particle, it charges with the radioactive source, and then kind of puts into a very high voltage, separates it. And once it separates it, you get one particular size, which you give it to the CPC, because the CPC then count the particles. So it will, so only a one particular size. So you take the sample, which is polydisperse, meaning that your sample contains all size of aerosol, like from 2 to 1000 nanometers. The DMA will separate it in each size range, like 2, 5, 6, 7, and the CPC will count one size, and this is how it gives you the size, where on the x-axis you have size and y-axis you have concentration, and then this distribution is the most important aerosol characteristic property in the climate. This is what the differential mobility analyzer. I'll not go into the detail in that, and this is how the size distribution looks like. Very quickly, Ashwati, can I take another 5 minutes?
Yeah, sure, sir.
Yeah. One of the very advanced, or the very kind of fancy one, is the something which is called as an aerosol chemical speciation monitor. So generally, whatever the concentration which you get using the filter-based measurement, that how much organic is there, how much ammonium is there, how much nitrate is there, how much sulfate is there, it is possible to obtain that in a real-time and online basis. So what this instrument basically is basically the combination of an APS, which I just told you, and then then a mass spectrometer. So what this instrument basically does is the following. It takes the particle from here, and then there is this vacuum chamber here. In this vacuum, there is a filament in this chamber. This is a vacuum chamber. These are the turbo pump. This is turbo pump 1, turbo pump 2. I think we operate probably 10⁻⁻⁶ star or something. And then here you kind of have a filament which is heated at 600 degrees centigrade. So it kind of looks into the particle which are non-refractory, meaning that any particle which get vaporized at 600 degrees centigrade. So the particles which comes in here hits that filament, get vaporized, and then this vaporization then goes into this spectrometer here. It is a real-time analysis. And then the spectrometer here will try to calculate the signal intensity of a given ion. And then that signal intensity is then converted to a mass by a very specific and extremely complicated calibration process. But the beauty of that instrument, that the advancement is that you really get the concentration of organics, nitrate, sulfate, ammonium, and chloride in microgram per meter cube in real time and online basis. Now, what is an advantage it provides you is that you can do the source apportionment, meaning that you can really pinpoint that what is the most toxic source in the atmosphere which is causing the health and climate impact. That's about it. Well, I mean, and then you could also use the offline sampling technique like an ACM analysis. Like, you can collect the filter samples on a filter paper and then kind of put it under the scanning electron microscope and like, go around to understand their size and then the behavior, like whether it is a pollen grain or fungal spores or whatever it may be. Like this is the study actually which Dr. Ashwati has done. I think she should tell you more about it offline. Yeah, and then you have this UV APS, which is again a very advanced equipment. I think Dr. Ashwati should be able to tell you. I'll probably gonna skip with that what it looks like. Yeah, I think that's it, Ashwati. I would also skip the PTRMS because it requires more time, but probably we can then try to take more questions if there are any. Well,
Okay,
thank you very much for giving me this opportunity, and I'll be happy to take more questions now.
Yeah, thank you, sir. So I'll directly go to the questions. So there are not many questions here now. So there is one question on sir, can you explain about the condensation nuclei?
Okay. So condensation nuclei is something which is a very, again, a bit of a complicated topic, right? But what I basically can try to tell you about the condensation is that which basically happens in a CPC here. So what happens is that where is my okay. So what happens in a condensation is that it is basically you have a particle example, Now, depending upon the size and chemical composition of this particle, which is defined by the something which we call as a Euler theory, an ability to take. Now, that basically defined by two things. One is by its diameter, which is called as a Kelvin term, and one is by the chemical composition, which is called as a Raoult effect, basically. Now, as I told you, is that when you have the water vapor, water molecule around it, around these particles, right? So there are two ways that a particle can grow. One is that all these molecules, they come together and then kind of find a bigger molecule, right? All these water molecules, they come and then form this bigger molecule. But that is not possible. Why it is not possible? Because the equilibrium vapor pressure over a curved surface, meaning that unless you have an extremely high vapor pressure, very high vapor pressure, you cannot keep those molecules, small molecules together, right? You have to compress it. So what happens is that they will keep evaporating. If the droplet is small, it will keep evaporating. It will keep evaporating. So what you have to do is that then in these water molecules, if you have a small aerosol particles, these molecules will kind of try to be replaced by some other solute here, right? So that basically kind of changes the Kelvin effect and then all that stuff, like, equilibrium vapor pressure is changed. So this is what is the condensation process, that depending upon the size and chemical composition of the particle, the water molecules will try to sit on that. And if once it crosses the very specific size range, the particle will start grow big enough. And that's what basically is the condensation process. I hope that I answered the question.
Okay,
Yeah,
sir.
next one.
So there is one more question. Despite of such advanced techniques in assessing these pollutants, why there is no synergy between assessment and mitigation measures? Why Delhi tops the list of having worse air quality?
Yeah, okay. That's a very interesting question. So what happens is that, I mean, the respected member from the audience used a very apt word, which is called as a synergy. So now what happens is that in my personal opinion, I mean, that is again me as a Sachin, and then anybody can differ from that. I believe that the implementation of the policy, like, and one always need to develop the policies which are strongly backed by the science. And I would like to quote a very classic example of Delhi, like where somebody has also asked this Delhi fog. So until now, we were kind of thinking that the smog in Delhi, not fog, smog in Delhi basically formed by the, like, the farmers are burning and it is coming from there. And then over the last 15 years, we always assumed that, like, when the PM 2.5 really goes up, the visibility reduces and so on and so forth. What we have found is that it is not only the PM 2.5 increase which causes the smog formation in Delhi. The very peculiar reason which we found in Delhi is the plastic burning. Now, in 30 seconds, I'll explain why this plastic burning. So what happens is that the plastic burning causes the release of hydrochloric acid gas in the atmosphere. Now, India being a very agricultural based country, a lot of livestock activities and farming and then use of fertilizer and other things also emits lot of ammonia over that region. Now that ammonia basically combines with the HCl to form the ammonium chloride particle phase. Now, what we found is that these ammonium chloride particles have an extraordinary ability to uptake the water. Then what happens is that in Delhi during the winter season, when you have the high humidity condition, these particles, they really swell big enough, right? Which they would not swell under the normal circumstances. And once, of course, these particles, they swell big enough, they kind of scatter the light and obviously your visibility comes down. Now, what we need to do then in Delhi is that we need to then cut down all the sources which will reduce, which will emit this HCl. Now, you said it very rightly that we now need to have a synergy between what we found and how to basically on ground you reduce the plastic emission, right? I don't know. I have no answer to that. I mean, I did my job by telling the reason behind it. Now, how and which way we implement this policy on ground is a big question. I don't have a direct answer to your question, unfortunately. Yeah.
There is another question, but can time of flight be used for real-time analysis?
Yeah, it is real time. Oh, you mean the chemical analysis? Oh, no, I don't think so. Because it just gives you the size distribution. But I do not know what the respected member of the audience mean to say that real-time analysis. I don't know.
Yeah. It is asked by Meena Kumari. So if you want better clarification,
nice. Yeah. Mm-hmm. Yeah. You can unmute and then probably say.
Meena Kumari, you can unmute yourself and you can clarify it.
Good afternoon, sir. This is Meena Kumari from Gunthe Engineering College. Yeah, so like I wondering whether I don't like analysis. So one part of it based on this acceleration and all. So yeah. Time of flight measurements, whether they can be like
for which
practice they are used in real analysis.
Yeah,
Meena Kumari, actually,
used, but it just
using these techniques for analysis, like where we can do it. Okay, sir.
Yeah. So it is being basically used for the size distribution measurement, right? So you can get something like this, like, you can have the diameter measured on the x-axis and you can have the normalized concentration on the y-axis. So what it basically does is that then you can assume the certain density in the, let's say you assume a unit density or 1.1, whatever it is, and then you can also convert it to the mass concentration as well, right? But again, as I said, that the problem with the time of flight is that this lower limit cannot be very low. You can hardly go maybe nowadays up to 300 or so something, because you have this constraint of the laser. You need to have a laser which will be able to see your particle, right? So yes, it is used for real-time analysis, but only for this kind of size distribution. You cannot really segregate, you cannot really collect those particles on the filter paper using time of flight.
So there is one last interesting question. So the question is how this air pollution is going to be destructive with respect to COVID-19?
Oh yeah, okay. Well, I mean, see, the air pollution, we did a lot of work on that and we are still doing it. So indeed, the air pollution is more destructive in type of COVID, and then it is not an overnight phenomena. So what happens is that the air pollution is a larger cause of comorbidities, right? And we seen that even anybody would tell us that the people with the comorbidities are not only vulnerable for kind of acquiring the COVID infection, but they are really suffering a lot. And then the vulnerability and then the mortality rate could also be high in the with the people those who have the comorbidities. And now this comorbidity is definitely it's associated with the pollution, right? Because more the pollution over the period of time, uh, the comorbidities will be developed into the people, and then any kind of this thing is possible. Absolutely. So there is a very strong relation because of the comorbidities resulting from the pollution, and this is how the COVID-19 on a broader scale is affecting to the people, more to the people those who have been exposed to the long-term pollution, and if they have any comorbidities which has resulted from the pollution. Indeed, yes.
So there is actually one more question. So it is like, is COVID-19 an airborne disease?
Well, it is also an airborne disease. I mean, it is majorly getting kind of transmitted by the people coming in contact and not really following the protocols, including the hygiene protocol. But yes, it is an airborne disease also. It is not only airborne, but it is also an airborne. But it is not really traveling for a longer distances, because virus is really very tricky business to deal with, right? So it's not that like somebody kind of sneezes here and it is traveling like 25 kilometers and somebody is getting affected. It's extremely, extremely unlikely. These are the fungal spores, because fungal spores are very resistant to the climatic factor, right? They don't die. Like any fungal spore which is emitted here can travel up to Delhi and then can affect a crop or a person there.
Okay, sir. So maybe, sir, we'll wind up with the question. And sir, there was one question previously asked on this isokinetic sampling.
Oh yeah, maybe I think can you just then ask? Can you just ask that? I mean, I do not really know. Can you see my screen?
Oh, sir. Actually, yeah.
It is an automated this thing, right?
Yeah. Just a minute, sir. I'll just.
No. Don't worry. No. Don't worry. No. So what I will do is that maybe you can ask that person to get in touch with me. For some reason, I can try to explain what is an isokinetic sampling then, because we don't want to really unnecessarily extend that for, like, I just completely forgot that because of the time.
Okay,
But
sir.
you can pass on my
I'll
details
just
to
ask
that
him
person
to,
and I'll send some material. Yeah.
Okay, sure, sir.
Good.
So thank you very much, sir, for this very informative talk. Actually, like, it's due to time constraint that you could not explain many of the things we know. So we wish that we could have given you some more time, but somehow we have to restrict all these recording sessions. Yeah, thank you very much, sir.
Thank you for the opportunity. Thank you, everyone. Thank you.
Thank you, sir.
Yeah. Okay. So can I log out now? Can I leave this meeting,
yes,
Ashwati?
sir. Sir, you can log out.
Yeah. Thank you very much.
Yeah, thank you, sir.
Yeah, poll has started for attendance, and the next section will start exactly at 2:30. So the section link will be active from 2:20. So you people can try to join little earlier. Thank you.
Yes, sir.
Is there any question?
Manoj Singh?
No, sir. No, I have already put my question in the chat box and he has given the answer.
Okay, fine. Thank you.
Sir, for the next session, new link will be shared or the same link will work?
No, same link will be. Yeah.
Same link, sir. Okay, sir. Thank you so much.
Yeah, so for all the sessions, the same link will be used.
Thank you so much.
Even for tomorrow also, you can use the same link to access the sessions. There is only one poll question posted. So you can just give your feedback that will be considered for your attendance.
Madam, the same question will work for our assessment, or there will be a different test for that?
That is different. So that will be after completing all the sessions. So we'll be having another test where you will be getting questions based on all these sessions.
Okay, ma'am. And we will get the PPT of the session?
We'll share the recordings.
Okay, ma'am. PPT will not be available.
The recordings anyway it is there. So if possible, we'll try to share the PPTs also.
Okay, ma'am. It will be better if it will be shared on the same day. At the end of the day, if it will be shared, that will be helpful.
Okay, we'll see how it can be done.
Thank you so much.